Katie Schuman. I'm at University of Tennessee. And this work is in collaboration with one of our PhD students who recently defended Charlie Rizzo and Garrett Rose and Jim Plank. So in our group, I don't know if this is true for other people, but in our group, we have like nicknames for papers that we're working on. And never once have I put the nickname of the paper in the title, but I felt like it was warranted here. So this is Embracing the Hairball. Looking at recurrence in spiking neural networks. So before I even get started, I do want to acknowledge that we are, our group, the co-authors and I are part of a much larger neuromorphic computing group at the University of Tennessee. You can see us here on the slide. We span doing research all across the neuromorphic computing stack within our group, and we are very sort of tightly interconnected doing co-design. So we do work from devices, architectures, software, algorithms, and applications. So all of our work is sort of through that lens of we're planning for hardware implementation, and when we're designing hardware, we're thinking about the algorithms and applications as well. And so if you're interested in learning more about our group, or you're a student, or you know of students who are looking for opportunities, we have opportunities for graduate students, undergraduate researchers from visiting universities, and even high school students. So if you happen to have a high school student in your life that would like to do neuromorphic computing research, send them our way. Come visit Tennessee for a week or two in the summer. So I'm so pleased that we have talked about recurrence a lot today, from Terry's talk this morning, through Friedman's talk, through various other talks. Recurrence has come up quite a bit. So I want to just go ahead and remind you, I don't have to tell this crowd this, but we're using recurrence a lot as it is in today's spiking neural networks. We're using them in things like liquid state machines and reservoir computing, typically having some sort of sparse, recurrent, randomly connected reservoir that's not trained. We just have the linear classifier at the end that we are training. We have winner-take-all networks quite a bit, used in a variety of contexts, typically with fixed weights. And we've heard several times today about using approaches where we're sort of taking concepts from recurrent neural networks in traditional neural networks and mapping those into spiking systems, either by doing a mapping approach after we've done training in the traditional system, or by having some sort of adaptation, surrogate gradient methods, things like that, to train in a spiking context. So in our group, we often end up with very weird hairball-like structures that emerge in our networks. And this is where I will note training recurrent neural networks is hard. But one of the things that we wanted to look at in this paper is it actually worth it to try to come up with these sort of sparse recurrent neural networks that you could deploy for different applications? So how we were going to evaluate this, we wanted to evaluate across control applications in particular, and we wanted to use a very simple spiking neural network simulator. Why control? Again, we've heard about it over the course of today. Control applications usually benefit from some sort of memory, but not all of them actually require memory to be successful. And as we've heard today, integrate and fire, leaky integrate and fire neurons have sort of a notion of memory just in the neuron itself, like the neuron itself almost gives you recurrence as well. So is recurrence in the form of, recurrent synaptic connections actually required? That's something we wanted to explore. So what we were doing here is we wanted to compare feed-forward networks with recurrent neural networks where any two neurons could be connected by a synapse. So to do this, and I apologize, many of you have seen this next sequence of slides many times, but bear with me. Here we go again. One of the things that our group at Tennessee, 10 Lab, does, because we do across the stack design, we have our own software framework that we do work with collaborators on. So if you're interested in plugging into our framework, please let me know. But we have a software core that defines common interfaces to neuromorphic processors, provides input and output coding. So it implements a variety of different types of encoding approaches and decoding approaches that can be used. And it includes a network compiler that you can define a bunch of networks that you actually want to connect together, and it will do that automatically for you. And to the bottom of our software framework, plugging into these common interfaces, we support a bunch of different hardware implementations. So in our group, obviously, we are also developing hardware implementations. Garrett Rose's team works on memristive-based neuromorphic hardware. We also design fully digital implementations. Our current implementation, Ravens, has both a digital version and a memristive version that we are currently fabricating. We also work with a bunch of different folks who are designing different types of hardware and looking at emerging devices. I've got a couple of them on the slide here. We support far more of these, but I have a couple that are sort of illustrative of we support any kind of hardware. There's a superconducting optoelectronic neuron implementation that we worked with some collaborators at NIST. That's SOANS. We work with an Oak Ridge team that's developed a fully digital implementation called Caspian. And then we've also worked with hardware is not the right word. I think wetware is the more appropriate word for the device, the biomimetic device, which is water droplets encased in lipids forming biomembranes that are acting as the synaptic device. So we plug into all of these sorts of hardware backends, and then we also support different simulators. External simulators developed outside our group like Brian, Nest, BindsNet, Nango, and Nango-Loihi. But in this work, we used RISP, which is a simulator that we've developed within our group. It's the Reduced Instruction Spiking Processor. It is implemented in simulation only, although we are actually also working on a hardware implementation of this. But in simulation, it is a C++ discrete event simulator. And the reason we used RISP is that it's blazing fast. It is very, very fast to simulate networks. It implements simple leaky, integrate, and fire neurons with programmable leaks and thresholds. In this work, we actually disable leak. And we allow neuron thresholds to vary between -1 and 1. You can also, in RISP, set it to be discrete values if you like. Here we're using more continuous values. The synapses have programmable waits and delays. So the delays in our networks are happening on our synapses, not on the neurons. But we allow the delays to vary between 1 and 5 in integer values, which are, of course, delaying the signal from the presynaptic neuron to the postsynaptic neuron. So this is the simulation environment that we used. In our framework, we support a variety of different training and learning approaches. We support Whetstone, which was a software package developed by people in the room from Sandia National Labs. We support a supervised STDP implementation, also designed by someone in the room from Oak Ridge National Lab. We do weird things like allowing decision trees to be trained using scikit-learn and just mapping those onto neuromorphic hardware, just for fun. And then we also support like reservoir computing. But in this work, we are using two evolutionary approaches. One is EONs. So this is an approach that I started developing as part of my PhD work, and that we've been iterating on for the last decade. And it is evolutionary optimization for neuromorphic systems. So this is the approach that we're using to examine recurrence in the networks. So EONs evolves the parameters of the network, but it also evolves the structure. So the way that it works is you have a particular hardware implementation or a simulator, in this case RISP, and you have an application that you want to address, a control application in this case. And we start with a population of randomly initialized networks. So in that population, all of the networks have the same inputs and outputs. The encoding and decoding strategies are a hyperparameter of the approach. So all of them talk to the outside world in the same way, but the connectivity and the hidden neurons are something that can be evolved as part of the evolutionary process, as well as all of the parameters. So what we do is we take a bunch of randomly initialized networks, we evaluate them on the application, which in this case entails loading them into the RISP simulator, running them on the application and getting a score. From there, we do, with those scores, we do tournament selection to preferentially select better performing networks to serve as parents. Then we do reproduction operations like crossover, which takes two individuals and creates children that inherit characteristics from both of those individuals, and mutations, which do random mutations to the network, both in the parameters and in the structure. So in this particular work, we started our population with either 0 hidden neurons, 1, 2, 5, or 10. And we turned off the ability for EONs to add hidden neurons. It could delete them, but it couldn't add any. So the maximum number in any of our tests that EONs was allowed to use was 10 hidden neurons. So this was the one that was looking at the recurrent networks. You can already see the types of networks that EONs evolves on a small scale. There's a lot of cycles and things going on in these types of networks. We then used another evolutionary algorithm approach just to sort of do an apples to apples. This was built on LEAP, which is Library for Evolutionary Algorithms in Python. It's an open source library that implements lots of different evolutionary approaches. And in this case, we looked at fixed structure feed-forward networks, so of the kind that you are used to seeing, and we evolved the parameters, so the thresholds, the weights, and the delays. Same inputs and outputs as we used in eons, and then we evolved the parameters. In this case, we fixed and evaluated networks that had 1 hidden neuron, 5, 10, 20, and 50. Now, let me tell you about the applications that we evaluated on. So in the 10-lab framework, we support a variety of different application types, classification, both static and temporal, event or anomaly detection, and also just sort of general computation style tasks. We focused on control in this case, again, because we feel like recurrence has the best shot in control of really having an impact. But if you have temporal data or you're looking at anomaly detection in time, recurrence also could help in those cases as well. So we looked at 3 simple applications. We have our own version of the canonical inverted pendulum cart pole balancing task, whatever you want to call it. And we looked at 2 versions of this task. One that includes the positions and the velocity information of the cart and the pole. Okay, actually, can I get, do y'all know, who knows what the pole balancing task is? Most people. You don't need me to explain this to you. All right, so that's the canonical version. The second version is the one without velocities. So the second version needs memory to be able to solve the task. So again, you're trying to keep the pole balanced, keep the cart from hitting the walls. If we're not giving it the velocities, it has to have memory in order to solve the task. The last application that we looked at used to be OpenAI Gems by Peter Walker. It's owned by another company now, but it's open source. And again, by Peter Walker, it's trying to control the walker to go as far as possible in the simulated environment. All right, so for each of our algorithms, for each of our numbers of hidden neurons, and for each application, we ran 20 tests with different random starting seeds. This is because evolutionary approaches are randomized search algorithms. So where you start in the search space will influence where you end up. So we have to run at least 20 tests to get any kind of statistical information about these. Each of our evolutionary approaches, we started with 100 individuals in the population, and we evaluated for 300 generations. Just to give you an idea, for one of these tests to do 100, population size of 100 and 300 generations, this is like less than 10 minutes for pole balancing, and less than 30 minutes for bipedal walker. So this is not very long, and that's when they're not parallelized. You can get them faster if you parallelize them. So we used 5 episodes in our training approaches to get the scores, the fitness scores for how they're doing in evolution, but the testing fitness that we report is across 1,000 random episodes. Okay, so what did we find? You're going to see this chart showing the results a lot over the next couple of slides, so I'm just going to walk you through it. So on the x-axis here is the number of hidden neurons. The yellow bars are the recurrent eons evolved networks, and the green bars are the feed-forward. The testing fitness is on the y-axis, and higher is better in all of those cases. So the first key observation that we found from this is that recurrent networks, the yellow bars, give you the best performance on each task. You can see that across these charts. The second thing to note is that our recurrent networks with 0 hidden neurons on average outperform all of the feed-forward networks. So if you allow for recurrence, you don't necessarily need hidden neurons at all. You could potentially get better performance than what you see with the feed-forward approaches. And as we expected, the pole balance approach with no velocities has to have recurrence in order to do well. So it was speculated, as somebody mentioned earlier, that sort of these integrate and fire neurons, and maybe LEAF would have helped, but the integrate and fire neurons by themselves do have some sort of temporal processing capabilities. With the delay in the network, there is still temporal processing capabilities even in the feed forward. It still needed recurrence to be able to actually get the results, any results at all. This is a harder problem. It needs more generations to train on, which is why the bars are not higher. But to get any traction at all, you need recurrence. So why was this paper called Embracing the Hairball? We're getting to that. It's also worth noting that Even tasks like pole bounce, where we know they do not require recurrence, this is pole bouncing with velocities, you don't need recurrence to do well in this problem. It still does better when it has recurrence, and it can do better with smaller networks. All right, so this is what one of the networks looks like. This is a pole balancing network with velocities. The input neurons are the gray neurons. There are 8 of those, 2 for each of the input values. And then we have 3 output neurons. Hit it from the left, hit it from the right, don't hit it at all. And what you can see, it's a hairball of connectivity. You've got synapses going in every direction. You've got inputs connected to inputs. You've got outputs connecting back to inputs. In this particular example, we don't have outputs connected to other outputs, but we do see that frequently in our other networks. But there are no hidden neurons at all to actually do well on this task. All right, now for a bigger hairball. This is a bipedal Walker network. It does have 2 hidden neurons in this case. Those are the purple ones that are up there. The input neurons are, again, the gray, and the output neurons are the blue. In this case, we have significant input-to-input connectivity. We have output-to-output connectivity. We have output back to input connectivity. And our hidden neurons are actually relatively sparsely connected. So these networks don't look like what you would typically see in, I imagine that outside of maybe reservoir computing approaches, you haven't seen spiking neural networks that look like this. So this paper was really in these simple tasks to motivate. Recurrence is interesting and we should look at it more as a community, but I wanted to give you some additional recurrence anecdotes from the work that we do at 10 Lab. So this is a network, and I will start the video, that we have evolved to drive a small-scale race car. That's not a bug on the screen. It is a tiny purple dot that's driving around that racetrack, which is an actual Formula One track. So we train in simulation here, but I really wanted you to see the network, right? So the input neurons are, again, the gray across the top. The outputs, we have more outputs than inputs in this case, are the blue across the bottom. We have one lone hidden neuron just all by itself in the middle. A huge amount of recurrent connectivity, input to input, output to output, output back to input. And we put these sort of networks on neuromorphic hardware to control actual systems. So this is that network deployed to the physical race car racing on a cardboard track that we built in our lab at UT. So we are actually deploying these sorts of networks for real world problems. Another example, this was actually presented at last year's NICE. So one of our PhD students, again, Dr. Rizzo, because he just defended, is working on neuromorphic downsampling of event-based camera data. And so he has applied his neuromorphic downsampling to event-based camera data pointed at Atari games. So we're not showing you the event-based camera mapping here. But after we've downsampled from the full Atari screen, with his approach, we're down to 48 inputs. This is the network that Eons evolved to play Pong using the event-based camera directly from the screen. 2 outputs here, paddle up, paddle down. And you can see this is the output of that particular network. Once again, a huge amount of recurrence and actually relatively few connections to the output neurons at all. And this last example is one that we did with some collaborators in nuclear engineering. This is work that was actually presented at ICONS last year. This is where we're applying neuromorphic computing to a anomaly detection task, in particular detecting radioactive sources in an environment. So in this particular case, you can see the input neurons across the top. That's where we're feeding in information from the spectrum of radioactivity that we're seeing. We have a full 6 hidden neurons in this example. 6 were required. For this one single output neuron that we're looking at the counts that are coming out of it to see if it's going above a certain threshold to flag as an alarm. So why did I show you these 3 examples? In all 3 of these examples, we are deploying these to actual neuromorphic implementations. And in all 3 of these examples, less so in the Pong one, although we still care about making it small. Smaller, fits on smaller hardware, which is more energy efficient. So having the smaller networks is actually really important to us. So even though we are having this recurrence that is maybe harder to implement in hardware, depending on your implementation, we can get really small networks that are still doing interesting things by leveraging this sort of recurrent connectivity. So for these three control applications, these recurrent networks can result not only in better performance, but also with significantly smaller networks, sometimes with 0 hidden neurons at all. And our main goal with this work was to demonstrate that allowing for more freeform recurrent networks can give better performance with these potentially smaller networks. Okay, but that's not really why I'm here. Here's why I'm here. I think that we should be developing new algorithmic approaches that can leverage these sorts of networks, because I don't have the knowledge to build the theory around why these work so well, but we're seeing it. Like, we're seeing the anecdotal evidence that it works. And I think we as a community, like, y'all are the smartest people I know, we could be making algorithms that are making these networks better and designing them, figuring out how to design them. So that was my plea of help me, please. We can be building networks that look like hairballs. They look like hairballs, but that's okay because they're smaller. They could be implemented more energy efficiently. And then the second plea to the community is, if you are a person who is designing hardware, think about these types of networks when you're designing your hardware, because they're pretty cool, and it would be nice to be able to implement them effectively in hardware systems that are being developed. So think about recurrent networks, not just the ones like LSTMs and things that you're seeing in deep learning literature, but think about the hairballs when you're designing your hardware moving forward, because I would love to use your hardware. I would love to collaborate with you. And I think these networks are cool, and these applications are cool and could take advantage of the really cool hardware that you all are developing. So with that, I will thank my collaborators, Charlie, Garrett, and Jim, and our funding agencies who supported this work. And now I have 3 minutes, so I will do a shameless plug. Shameless plug. So I'm the general chair of ICONS, the International Conference on Neuromorphic Computing Systems. It is going to be held in Arlington, Virginia, July 30th through August 2nd. And the main reason I'm telling you about it is the deadline to submit for ICONS is 1 week from today. So this is your reminder that you have 1 week. And I understand that you're here at this conference, and you're definitely not working on your computer while you're here, but the deadline is 1 week from today. So, and we won't be extending it. So I apologize. This is normally, April 30th is normally our extended deadline. But this is the final deadline. So please submit your work. We would love to see you at ICONS in July. And if you have any questions about ICONS, I will be here for the rest of the afternoon. So please feel free to ask me any questions during that time. All right. Thank you so much for your attention. Happy to take any questions you have.